Okay, so here's an example of setting up a hypothesis test for difference between two populations, matched pairs. Efforts are made over a 5-year period to improve the clarity of the water in a lake. Water clarity is measured by recording the depth at which an object is still visible from the surface. A researcher takes measurements at the same location and date, by which I mean day of the year, so 5/11 or 7/13. So same location and same day of the year, but the measurements are 5 years apart. Is there evidence at the alpha equals 0.05 level of significance to indicate the lake water is clearer after 5 years? So what are our hypotheses going to be? Well, the null hypothesis will be that there is no difference, that the average difference in water clarity is 0. So in other words, I'm just going to make a note up here in words. What is it that we're saying here? This is saying same clarity before the 5-year project and after the 5-year project. H1, let's see, we're being asked to test, is the lake water clearer after 5 years? So more clarity after 5 years. In other words, you can see deeper into the water after 5 years. Now, I'm not going to put the mathematical inequality here. We're going to need to come back to this because what we write here is going to depend on how we set things up. Okay, so we'll come back to this. Let's look at the data right now. So what's going on here is again, there's some location that's the same all the time. Otherwise, different factors would affect the clarity because it's different in different locations. So we've got this one location where we're checking the clarity, and we're also, the researcher also is using the same date of the year. So like maybe this is 5/11 the year 2000, and then 5/11 of the year 2005. So after 5 years later, depth 5 years later. And that's important because water clarity also varies with the time of year. As an example, if you have you have snow melting and extra water flow in streams, then you're going to have more mud and silt being plowed into the lake because of the spring flooding, spring extra water coming in, and those conditions are bringing more silt into the lake. So that varies throughout the year. So that's why the samples here we have are sort of categorized by day of the year, but then for each day we have this pair of samples. So this is matched pairs because as soon as I've picked 5/11 as the date I'm using initially, then that dictates that I'm going to use 5/11 as the date 5 years later. So these two go together because they're from the same day. So these are a matched pair. And again, with this matched pair setup, what we're going to do is we're going to calculate the difference for each pair. So I've got a column here for the difference, and that's what we've been calling D. Okay, so let's put that information in. So so you have a choice here. You could do 38 minus 52, or you could do 52 minus 38. Now, I tend to like doing things from left to right, so I'm going to do 38 minus 52, but you wouldn't have to do it that way. So 38 minus 52, the difference is negative 14. 58 minus 60, I'll get a negative 2. 65 minus 72, I'll get a negative 7. 74 minus 72 is 2. 56 minus 50, 56 minus 54 is also 2. And then 36 minus 48 is negative 12. 56 minus 58 will be a negative 2, and 52 minus 60 is negative 8. So this difference D, again, maybe I should make a note of that in the heading here. I probably should, so that I know later what I've done. This difference, the way we got this was by doing initial minus 5 years later. Okay, and I'm making a note of that because you could have done it the other way around. So it's going to make a difference. Because notice if I had done it the other way around, 52 minus 38 is positive 14. 60 minus 58 is positive 2. I'd have basically the same numbers here, but with the signs changed. So anyway, it's this difference that I'm thinking of as my variable now, the difference of each pair. So when I compute the mean difference, that's the mean, the average of these guys. Okay, so that's going to work out to be minus 5.125. Again, that's just the average of these. And then the standard deviation of these differences, because we're basing everything off this variable D, the standard deviation, which again the book calls S sub D. I'm not going to bother with that, but if you see that in the homework or the book, it's just indicating that we're working with this difference variable. The standard deviation turns out to be 6.081. So let's notice that before we go back and fill in what the alternate hypothesis is, let's notice that because we've done initial depth minus later depth, that's negative, less than 0, when the later depth is larger. Right? If I subtract a larger number from a smaller one, that's when I get a negative answer. So I'm going to have negative answers when the later depth is a larger number. In other words, and remember, having a later depth be larger means that you could see further into the water. So the water is clearer. Okay, so it's when this difference is negative that we have clearer water. So if we go back to our hypotheses, okay, we never filled in the alternative hypothesis. We're testing for more clarity, deeper visibility into the water, and because of the way we set up the difference, that's going to correspond to having a negative difference. Now, if we had instead computed, if when I did the subtraction, I had instead gone later depth minus initial depth, then the alternate hypothesis would have been that the difference is positive, because here you'd get positive answers when the later depth was deeper, when this is the bigger number. Okay, so you kind of have to think about, with these differences, you have to think about what am I doing when I subtract in one order rather than in another order. Okay, so let's put some numbers in now and get an answer here. Okay, so here's the formula for our test statistic. D bar, that's the mean of the differences in our sample, and that we computed to be negative 5.125. The standard deviation was 6.081. Sample size N was 8. And what I'm going to enter into my calculator is, and I'm not even going to bother with the minus sign to tell you the truth. I'll just tack that onto my answer afterwards. So remember, when you divide by a fraction, it's the same thing as inverting and multiplying. So I think what I'm actually probably going to do is do 5.125 times the square root of 8 over 6.081 and see what I get. Okay, and doing that, I will get negative 2.38. Okay, so that's our test statistic, and again, he typically calls that T naught. That's our test statistic. We use that to get the p-value, the probability of having the observation that we got, having the data that we got, based on assuming that the null hypothesis is true. Okay, so I'm going to be looking at the t-distribution with 7 degrees of freedom. Remember, the degrees of freedom is 1 less than the sample size. 0's in the middle of the t-distribution. The test statistic we got was negative 2.38. Now, the t-table gives you area, so I want this area. That's going to be my p-value, is that area. The t-table, though, doesn't give areas to the left. It gives areas to the right. So what I'm actually going to be getting, looking up, is 2.38, and what the table's going to give me is the area here, but that's the same as the area there because the t-distribution is symmetric. So anyway, if you look this up, you'll get, this is approximately, you can't find exactly 2.38 on there, but the number that's closest to that will give you area 0.025. Okay, so that's, similarly, that's the same as that area. Okay, so the p-value is approximately, what did I just say? 0.025. Now, what do we do with that? We compare it to the level of significance, alpha. What was alpha? That was, we were asked to use the 0.05 level of significance. And so remember, the question is the p-value bigger or is alpha bigger? And in this case, alpha is bigger. When the p-value is less than the level of significance, that's when you reject the null hypothesis. And our conclusion then, which we state in terms of the alternate hypothesis, and by rejecting H naught, we're concluding that there's evidence to support H1. So that's what we'll say. There is sufficient evidence at the alpha equals 0.05 level of significance to indicate the water is clearer, the water is clearer after 5 years. Okay, so that's the hypothesis test for difference of matched pair means. I think we'll stop here and we'll come back and do a confidence interval.